So this is the last part of our first chapter one, and we're just going to go over some properties that you can get straight from the point group. A lot of the information that we get from the point group, we'll use it in problem solving to solve more complicated problems later in the course with respect to spectroscopy and other chemical problems. But there are two things, chirality and dipole moment, that you can get straight from the point group. And so you may remember from probably your organic chemistry course, right, that chiral molecules have handedness. That means just like your left and right hands, they cannot be superimposed on their mirror images. Rigorously, what this means from a point group standpoint is that you don't have any inversions, you don't have any mirror planes, and you don't have SNs. And so you may have learned that, you know, chiral things don't have reflection, reflections, and things that aren't chiral have reflections. That actually isn't true. That's not a correct definition, and there are some examples that I'll show you where that isn't true. So yeah, most of the time it is true. So the absence of sigma planes most of the time tells you that you're chiral. But a chiral molecule can also have an SN, okay? So the easiest thing to do is I can just tell you which molecules in certain point groups are chiral. And the only ones, there's only a few. There's CN, DN, T, O, and I. And so all of those point groups will be chiral. Something that's asymmetric, just a little bit of nomenclature here, means that there's no symmetry beyond E, so that would be a C1. But dissymmetric means you have E's and CN's only. So C2, right? C2 point group has a C2 rotation and an E. And so we call that dissymmetric. But C2 and C1, both of those would be chiral. If you're not in CN, DN, T, O, or I, all these are fairly rare point groups, especially T, O, and I, you're going to be not chiral, okay? And so here's an example, this carbon monoxide complex of cobalt. This is chiral. It does have some symmetry elements beyond identity. It's point group C2. There is a C2 right here, but it is chiral. This is just showing you how the different oxygen atoms transpose. But there's no mirror plane, so that kind of tells you well, probably it's chiral. But importantly, there's no SN also. No mirror planes and no SN. And so the mirror planes are not superimposable, so it is chiral. But it does have a C2, so there is some symmetry there, right? So we call it dissymmetric. Here's an example of something that doesn't have a mirror plane, but also isn't chiral. So your classical organic chemistry definition here would mislead you, looking for a mirror plane. This is an S4 point group molecule, tetrafluorospiropentane. And it has the following symmetry elements: S4, C2, what I'm calling an S4 to the third. That means do a S4 3 times, okay? So, and it has also an identity, right? So you can see this S4 here, we're gonna do a C4, so this green atom's gonna, the fluorine, is gonna go over where this hydrogen is, and then it's gonna flip down because we're doing a sigma H. We do a C4 followed by a sigma H, a mirror plane. So this green atom went down to this green atom, and they all superimpose. So there's no mirror plane in this molecule, but it's not chiral. So that's a very, again, odd example, but it just shows you what the definition really is of chirality. No S's and no mirror planes. Next, we can go over for permanent dipoles. And so the point group can tell you whether or not you have a dipole moment. The way to do this is think of a dipole moment as having a single-headed arrow. Probably that's how you've done it before. And in order for the molecule to have a permanent dipole moment, that arrow cannot be affected in any way by any symmetry operation, okay? So if you go through this, molecules with sigma H, inversion, SN, or the D point groups, C2 perpendicular to Cn, can't have permanent dipoles. The only one that have permanent dipoles are CS, Cn, and CNV. And so the reason is because these point groups have symmetry operations that can change the direction of that dipole. These don't, okay? What will end up happening is you'll have a dipole and it'll just kind of rotate in the plane or along the axis of that dipole moment, and so it won't change. And so, you know, I'm not really going to test you a lot about dipole moments, or I don't think at all about dipole moments, at least on exams, or chirality, maybe on the homework. But I just want you to know that there are some properties you can get from point groups, but they aren't many. Usually you have to do much more sophisticated calculations, which the rest of the course is going to.